So welcome everyone to the first seminar for the Net Zero Interdisciplinary Series. My name is Grazia Toreschini and I am a reader with the Department of Engineering at King's College London, and I'm the coordinator of this seminar series. Um, I hope you know about the Net Zero Center. So this is a new initiative from the university trying to bring together researchers with a common interest in all areas related to net zero. And it is hosted by the Faculty of Natural, Mathematical and Engineering Science. And as part of the activities of the center, we host seminars. Now the seminars are going to be online for a couple of months, and then we will have some in-person events. Today, I'm very pleased to have Dr. Patel, who is a new lecturer at the Department of Physics at King's College London. He earned his degree from the University of Warwick in 2014 and the Doctor of Philosophy at the University of Oxford in 2019. And then he worked as a postdoctoral researcher at the National Renewable and Sustainable Energy Institute. That is a collaboration between the National Renewable Energy Laboratory and the University of Colorado. From 2022 to 2023, he held position as a Dave Clark EPSRC Fellow and Fulford Junior Researcher Fellow at the University of Oxford. And he joined King's College London as a lecturer of Functional Photonics in 2023. And now his research focuses on advancing multi-junction perovskite solar cell with a high power-to-weight ratio. Today he will give us a talk about this topic. You can see the first slide already on the screen with title Low-Cost Multi-Junction Photovoltaics. Just a couple of housekeeping details. We will have a little discussion at the end of the seminar. So if you want, you can hold on your questions until the end or feel free to type them into the chat. We try to have, if possible, a discussion. So if you want, we appreciate if you want to talk and discuss with us, but if not, I can also read the questions from the chat. So without further ado, I leave now the floor to Dr. Patel and I look forward to your presentation.
Thank you. So, hello everyone. Today, I will be talking to you about photovoltaics and specifically multi-junction photovoltaics. And it's something that is, a very important part of reaching our net zero goals. And even beyond that, when we, there is very little carbon emission. And multi-junction photovoltaics have always existed in the sense that we've put them into space, but they've been very expensive. So you've not been able to use them on Earth for applications to generate power for civilization, let's say. So what I'm going to talk about is perovskite photovoltaics, and you can see that the crystal structure of perovskites is shown here. And I'm going to talk to you about how this material can facilitate us creating low cost-effective multi-junction photovoltaics. And I'll tell you the importance of why multi-junction photovoltaics is important in the whole scenario of the energy landscape. So if you actually look at the cost of a solar cell or a solar panel or a solar installation and what it consists of, what you see is that the whole installation has these costs where it's the labor costs, you have the installation costs, then you have the hardware and the inverters, which are all fairly defined in value. There's not much more innovation that can go into them. However, modules, which make up just about a third of an installation, there is a lot of innovation that you can do. Suppose we can actually reduce the cost of a module by half, and that will significantly decrease the price per watt of solar energy. And so this is where I work on, and this is what we, as a community in perovskites, have been actually really trying to tackle head on into reducing the cost, reducing the price per watt of a solar module. And so the way we do that is actually by designing a new solar panel which has different materials on top to harvest the energy better. So existing solar panels, the ones you see on the rooftops currently, and which is the most widespread technology, is silicon. You use silicon, single crystal silicon, which requires a high energy process. And the current maximum efficiency you can get from silicon is 28%. And you can see over here, the world record in a research laboratory is around 26%. And that's in a very small scale. And typical panels that you see on rooftops are around 20%. And what this means when I say just 20%, I mean it converts 20% of the solar radiation into electricity. So if you actually think in how these photovoltaics work, the existing panels, you have a slab of silicon in the middle that absorbs all of the sunlight above 1100 nanometers. So you have the infrared, the red light, the green light, and the blue light. It's all absorbed in one material. However, the way light works is the fact that blue light has a lot more energy compared to the red light. And if you absorb all of the lights in one material, you actually lose the energy of the blue light through thermalization, which is just lost as heat. A way to make a solar cell more efficient and surpass the theoretical maximum that you can get in a single junction is actually design a solar cell that absorbs each color of light separately. And so as you can see here, you have two materials that absorb different colors of light. You have one material that absorbs the blue-green light and the other material that absorbs the red and the infrared light. And what you get in this particular configuration, or this one over here, is that you actually start to see that the efficiencies that you can get here, so the PCE is the power conversion efficiency from light to electrical energy, you can see that you can actually surpass the maximum limits of a single junction, which is 33%, to 46%. So already we can now have a solar cell that has the potential to be far more efficient, and therefore, if it converts more solar light into electricity, then your module cost is going to be lower. But that's only if the materials that make up this absorbing layer cost very little, and it doesn't take much energy to create. So, as I said, theoretical efficiencies can increase as you go into two-terminal tandem. So you have two absorbing layers, one for the blue and one for the red. Now, to create such a multi-junction device, and to make sure that it's cost-effective and actually does change the whole landscape of the solar energy field in terms of people will start to implement it straight away, you need a material that you can tune the band gap. And in this, what I mean by the band gap is that the band gap of a semiconductor is where you excite an electron from one of the bands into another band, and the excitation is dependent upon the color of light that you shine upon the material. So if you change the band gap, you can say, now this material only absorbs blue, or it absorbs red, or it absorbs green. So you need a material that you can easily do that. You need a material that absorbs the sunlight or any light highly. So it's dark, it has a coefficient that it can absorb light very, very effectively. Now, once it's done the absorption process, you need a material that allows the electrons to move freely to the electrodes without getting lost in the material somewhere and then relaxing back down to its ground state. You want to excite the electron that's been excited by the sun, and you want to take it out and use it in your application. So the material needs to have excellent optoelectronic properties. And as I said earlier, you need to have cheap materials too to make it cost effective. And you want to create a material that can be easily manufactured. You don't want something that's really hard to make and it won't really work when you upscale it. And then it comes to the durability. Current panels can last 20 years with very little losses in terms of performance. And so what you'd like is ideally a material that you develop that, of course, it's sensitive to light. It's a solar energy material, but you also want it to be durable under heat. and you want it to be durable under moisture, as the environment consists of all these different elements. So this is what makes an ideal photoabsorber for a multi-junction device. It's an interplay between optoelectronic properties and the fabrication, and how you can fabricate it, and the durability of the said material. So let's look at optoelectronic properties. What material actually allows us to have such a range of optoelectronic properties that are beneficial to create a multi-junction device? And that's where I come upon metal halide perovskite semiconductors. It's a material that perovskites have existed for over a century, but metal halide perovskites, which consist of this crystal structure where the A site has an inorganic-organic hybrid element. You have a central metal cation that's either lead or a tin, and you have these halides that are at the faces of this cube. This material has actually proven to be very, very tunable. As you can see in the figure on the right, you can change these different compositions, elemental compositions, and you can actually start to absorb different colors of light. You can see when there is very little iodine, but lots of bromine, you start to absorb only blue light. But if you add a lot of iodine and not a lot of bromine, which has a smaller atomic size, then you start to absorb a lot of the red and the infrared light. And so this property of metal halide perovskites is incredible. It now allows us to create this tunable material that can absorb different colors of the light, and therefore you'll be one step closer to attaining a higher efficiency solar panel. Now it comes to the optoelectronic properties. What about how do perovskites do in terms of optoelectronic properties? Well, it has a direct band gap, which is important. So an excitation, a photon-mediated excitation, results in an electron going straight into the conduction band. You have a low effective mass, so there's a relatively high mobility of the electrons, so they can move across to the electrodes quite fast. And then it comes to the amount of traps. The material has shown that you can process the material in very low temperature synthetic methods, and the traps that form, and traps are defects that occur on these crystal lattices where the charge carriers are not actually trapped. And essentially the traps are benign, and the charge carriers can actually diffuse to the electrodes, and you actually get a really high photocurrent and a high photovoltage. These are all important aspects into making a good photoabsorber. One last thing is how the material does upon photoexcitation. One concept in physics is that one would say, okay, you excite an electron, the photon excites an electron, but how tightly bound is it to the hole that it's left behind? And that's dependent on the material. So organic semiconductors, the electron and the hole are very tightly bound, and instead of the electron being extracted, they usually recombine, and that's called the excitonic binding energy. In the case of perovskites, we actually calculated the binding energy to be much, much lower than room temperature. Therefore, if you actually do the calculations, you find that when you illuminate using the same intensity as the sun on this perovskite material at room temperature, all of the excited electrons are free to move wherever they want, rather than be tightly bound to the space that they've left behind. So this all bodes really well in terms of the intrinsic physics properties of these materials. How does it do when we actually start processing it? And so then we come down to fabrication. Now, usually what fabrication involves is people say you can use a solution-based method, or you have inkjet printing, or you can use a dry method. And what I specialize is in the dry method. And the advantages of the dry method and of physical vapor deposition is that you can coat large areas, you can do a conformal coating, and you can really tune the thickness of your absorber. Now, this is a technique that OLED TVs are made from, and you can see how big OLED TVs have become these days. Therefore, this technique is already industrial already. People use it in industry all the time to manufacture in large scale, large area electronics. So this technique in itself is very important. And if we can make the material that we've developed in the lab to be used using this physical vapor deposition technique, then actually whatever we develop in the lab can be fully translated into industry and then developed into a product. Now, the disadvantage of this technique is it's an expensive technique to start up. You need high vacuum equipment, you need glove boxes, and therefore it does take a lot of upfront cost. And it's also challenging to optimize because you are relying on PID control and just computer control rather than more traditional synthetic routes where you are just spinning it or controlling the flow of ink. So how does a physical vapor deposition system work? Well, in the case of perovskites, you have different sources in this chamber, and the chamber is pumped down to high vacuum. And what happens is you have an organic source and an inorganic source. And the organic source evaporates an organic precursor, the inorganic source.
Yeah.
Okay, so I was saying we have an organic source and an inorganic source, and essentially what happens is that these materials are evaporated simultaneously, and you get a reaction on the surface, and you form this perovskite material that I said earlier. And initially, we were really curious because this is a new type of material and how actually the crystal grows. And so what we did is we did an experiment, and we actually tapered the time to actually. We took the samples out at different time points during this reaction. We started to see, okay, how does the material form? What is the actual crystallization mechanics of this crystal growth? It's a relatively new material, and we weren't sure how the inorganic and organic hybrid element will play in to the growth of the material. And what we did is we, as I said, we took some samples out, and we can see here in the absorption spectrum that you can see here, you can see that the absorption increases as you increase the thickness of the material. And so there is some material that's been reacted at the very early stages, and it's formed the perovskite. And what happens afterwards, we did diffraction analysis, and we started to see, okay, how big are these domains that we are forming? Essentially, what happens when the materials react? Do they instantly form small little islands? Do they form structures which are strained? Or do they form something which is just an amorphous blob? But what we found is actually what the reaction induces is that there is an actually crystalline product that's formed onto the surface of varying different sizes, as you can see in the bottom graph at the bottom where it says the crystallite height. You can see that it slightly increases, but at the very initial stages, it all stays pretty same. What we did to actually understand what's happening at these very small thicknesses is we said, okay, let's do a photoluminescence experiment where we actually shine light on the material and we see what light is emitted by the material. And what we found is that actually at the very, very thin films that we grew, the photoluminescence shifted. And what this means is that there's a quantum confinement effect. Because the crystallite sizes are so small, the band gap has actually increased, and you actually see a blue shift in photoluminescence. And using a combination of all these results, we were able to build a picture on how the crystal grows. We realized that initially you get these island crystals where you can get confinement of this light, and you get a change in band gap. And thereafter, after you've completely covered the substrate with these small islands, you start to form a thin film that can absorb light really effectively. So this is something that's trying to understand how the crystal growth mechanism works. Now we know that we can make this material. So what happens next? Well, let's see how we can make it into a device. And I'd like to reiterate that this is a single junction device. We are not going into multi-junction yet because we're just trying to explore the properties of a single junction device. And so I made a whole range of different devices with different thicknesses. And you can see here that, the technique really does allow us to control the thickness of the material quite precisely, which is something that's important to make sure that we can absorb the maximum amount of light in a solar cell. What else we found using this technique is actually when you do create these thin films, you start to see an interference effect. And this is well known in thin film optics, because when you form a thin film, you have a Fabry-Perot effect, and you actually form an internal optical field. So what happens is the light goes into the device, reflects back off the metal electrode, comes back. And if it's not absorbed, you'll start to see a formation of standing waves. And you can see that here clearly. The thinner the device, more of the light comes back from the metal electrode, and you start to see the formation of these standing waves. And you really have to make sure that you tailor the thickness such that there are no standing waves and all of the light is absorbed effectively. And so we did some light management modeling to understand exactly what thickness is optimal to absorb the most amount of light, but also extract the best optoelectronic properties. With that, we got a good device efficiency of 20%, and we were like, okay, a material system works. We are now on par with what traditional silicon is. Let's look at the durability of the material. And so the durability of the material is something that I really heavily looked at the National Renewable Energy Lab, where they really do have expertise in putting through a whole range of solar energy technologies and seeing how they do in different environments. And the two environments that I focused on is partial shading and actually the temperature or the climate and how that affects the devices. So what do I mean by temperature? Well, a solar cell goes through different temperatures throughout the year as there's climates in different parts of the world. And so you'd want to know what happens when the temperature heats up or cools down. And the metric that people use in terms of the solar industry uses the temperature coefficient. Essentially, that means how much of your performance do you lose or gain as a function of temperature. So first we just measured how a material changes in terms of its band gap. So what happens in materials, in semiconductors, is when the material gets warm, things expand, and when the lattice expands, the band gap usually goes red shifts because of the different orbitals that interact. But in perovskites, we found actually it was the opposite. You can see, get the laser pointer. You can see over here the gallium arsenide and silicon, the traditional semiconductors that you have. You can see that the band gap is red shifting. However, with the perovskite, it's blue shifting. And what we found is actually what this does, what the implications of this in the device is that intrinsic carrier concentration, which always increases as you increase the temperature, will actually be dampened for perovskites. So this is great news. What it means essentially that there'll be less of a temperature effect there'll be less of a change in performance as you change the temperature. And so we actually took these measurements and actually made devices and actually looked at the devices, and actually it all matched up pretty well. As you can see over here, the temperature coefficient of perovskites is on par with the very best technology that is out there in terms of solar technology, which is gallium arsenide, which is a near perfect material when it comes to absorbing light, very expensive. And perovskites, which are made very easily, they're really cheap, have a similar type of temperature coefficient, which is excellent news as we try to, try and mass manufacture this material, which has properties that are on par with the very best that's out there. So if it has such a great durability in temperature or behavior in temperature, what does that mean when we compare it to the existing mass scale technology? So we actually did an energy yield model, and we found that the current best perovskite module that's out there, which is 17.9, which has increased recently, but at the time it was 17.9, How would that compare to the current best silicon panel that's out there, which was 20.4? We actually found, because that the perovskites do so well under the changing temperature, the actual energy yield, the amount of energy that you generate throughout the year, will actually be very, very similar. And so this says, if the perovskite modules are better than silicon, which they will be based on the maximum efficiencies that you can attain, then they will produce far more energy throughout the year. So that's good news. And I have put an asterisk here saying, assuming they have same stability as silicon. What I mean by stability is perovskites have not proven that they can withstand the ins and outs of the climate for 20 years. That's something that there's a challenge that people are working on. The second thing that I looked at was the partial shading effect. And what happens in partial shading is, if you can see in the modules over here, you can see part of the module is illuminated and the other part is dark. The part of the module that's illuminated still generates current. Now, the solar cells are all connected in such a way that you need to allow this current to pass through. And therefore, to do that, these dark panels go into a negative voltage to allow this current to go through. Now, in silicon, that's perfectly fine. It has no problems in passing the voltage, changing the voltage and passing the current through. We were curious to know what happens with perovskites. And what we actually found was, with perovskites, when you took it to a negative voltage to allow the current through, in fact, the devices lost a lot of their efficiency. They lost a lot of their ability to convert sunlight into electricity. And what we believe is happening, and what the reason for this is, essentially that there's all these electrochemical reactions occurring, which halides are known for, and causing all sorts of different types of irreversible and reversible degradation. And so that's another area that, as a field and a community, we are working towards in providing better solutions and making the device more stable. So moving on from durability, now we want to go into multi-junction process. We're like, okay, this material works fantastically well as a single junction material. Let's see what we can do with a multi-junction. And you can see here, I said silicon has reached around 26.8 as a single junction. What happens if we put this perovskite material on top of the silicon? And recently, the biggest manufacturer of solar panels in the world, as shown here, announced that they got 33.9% module, which is incredible. We've already now not surpassed 26.9 in the small margin. We've smashed it. And so we are now on the verge of saying this is a very commercially viable technology in terms of putting the perovskite on an existing silicon module. But what about if we want to increase this number even further? And that's where my current EPSRC fellowship is based on, which is developing triple junction photovoltaics. We're going to take that double junction a step further and push to a triple junction, which is a theoretical limit of 52%. So this technology has the ability to, let's say, give us 46% or 45% of solar to electrical power conversion efficiency, which would be a huge game changer in terms of using PV across the world. So how does that go? Well, I've shown you how we developed the material in a single junction way, but now we need to develop this really intricate multi-layer device, which incorporates 3 different perovskites that absorb 3 different parts of the spectrum. And not only are we planning to do this in this, the fact that the perovskites can be formed in the thin film, we can actually have them on flexible substrates, meaning that they can be placed far more easily than mounting them on a huge metal weighty object like you do with silicon panels. So how does that work? Well, my focus right now is developing the material that has the widest band gap and absorbs blue light particularly. And I want to make sure all of the blue light that's absorbed, that you can extract the maximum energy out of it. Now, as you push the band gap wider, it becomes harder to develop the material because there's more chances of there being defects, which will be in between the gap, lowering the voltage. So that's a challenge. But how do we make such an intricate structure? We can't just use one chamber where you take it in and out around 13 times. And that's where the National Thin Film Cluster Facility comes in. That's something that the EPSFC has developed, and it's based around the Department of Physics in the University of Oxford, which is where I predominantly do my experiments at. And they've developed a whole facility where you have all these different chambers, where you can develop all those 13 layers, in theory, with the press of a button. But in reality, it's not been that easy. And it's a huge tool where you load the samples here. Everything is in vacuum, and substrates go in all these different chambers with these to grow all these different thin films to eventually develop that intricate structure that I said and I showed earlier. So it looks like this. As you can see, there's many different aspects to it, and one of the key aspects is that it has a robotic tool that you can essentially not break vacuum. And that's important in the sense that what it allows you to do is move and create substrates and thin films where the surface of the material does not change, as it's all under vacuum. And that will allow us to create a device which has very minimal surface defects and essentially allows to produce a device that will have a high efficiency. So as you can see, the robotic arm does everything. It's pretty much replaced me as a human, but that's fine because there's a lot of intricate physics that's still to come. For example, I've shown that, okay, I use this facility to actually develop all these different compositions of perovskite in one run. That's fantastic. Now it's cut my workload in this particular case by 25 times. Previously, I would have had to put in the substrate each time, fabricate the materials, each of these materials in a single deposition. Now you can do them all in one go. But is this enough? So I would like to make a material that absorbs all the blue photons. And so as you can see here, I did the photoluminescence spectroscopy where you shine light and light is emitted, and that emitted light is representative of the band gap. And you can see over here that the photoluminescence spectra says, I've developed a material which has 2 electron volts, which is ideal for the triple junction. And how good is this material? Well, actually, if you look at this material and zoom in on it and scan for a longer period of time, you start to see this shoulder that appears on the very right of the spectrum. And what that shows is that there's a new material forming or something else forming that's emitting at a lower wavelength. And as I said earlier, anything that doesn't emit from the wide band gap is somewhat of a trap or another state that reduces the voltage. And that's something you don't want. So as I've shown you, I've developed these materials. However, now you can see that there's another challenge, the challenge where you shine light and you see the formation of this new material that's forming. And we call this photo-induced halide segregation. So moving on, we actually looked at the physics of it, and it's currently a very hot area of research. And what we did is we used ultra-fast lasers to actually see what happens to the intrinsic properties of these materials as this material is evolving and forming another segregated state. We find that because this other segregated state has a lower band gap, all of the electrons that you generate in the bigger band gap material, wider band gap material, all funnel in super fast into the lower band gap material, which emits. Now, this is a source of voltage loss, but actually it's not as bad as we think it is, because of this effect of the tunneling, or funneling, I should say, the amount of domains that actually form in terms of the low gap material is not that much. So in general, I've now come to pretty much a conclusion. in the sense that I've shown you that, okay, triple junctions are good, but I've just showed you the previous slide is state of the art in the sense that, okay, this is where we're at. We can develop this material using a technique that's industrial already. We are now very close to making double junction devices. Oxford Photovoltaics, which is a company based around Oxford, that actually makes perovskite silicon double junction devices. But when it comes to triple junction devices, we have the technology to develop the material, but now there are material intrinsic properties that challenges that we face there in terms of stability that we are looking at in the community. And one thing to note here is, as we develop this material, we found that this material can be used for an array of different applications. One example is using healthcare devices. So healthcare devices require a material that has a high Z number, so lead, cesium, iodine. It absorbs a lot of the X-rays. And the fact that we can tune the band gap, we can make a detector that's operated at room temperature. Now, if we actually go to a hospital, all of the CT scanners and PET scanners require liquid nitrogen cooling or cooling. And that's a very highly energy intensive process. So replacing them with something that works at room temperature, you're already going to reduce the amount of carbon emissions from that particular hospital. And so this is something that we've been looking at, and that's something that we've been going towards that with a secondary application from the research that I've just shown you. In that, I'd like to conclude and say thank you for listening. And so apologies for my laptop deciding to restart.
Thank you very much for your presentation. And I think most of us are used to laptop restarting at random times because of the way they're set up. So we completely understand that. So it was just a short interruption. So I really want to thank you because this talk was very interesting and fascinating, and really your research is obviously cutting edge in this topic. The facilities also you showed are amazing. I didn't know they had such a type of facilities there. So I want to ask now if there is any questions from the audience. You can raise your hand if you want, or type into the chat. Yeah, I can see a hand up. I don't see who that belongs to. David Richards. Yes, please.
If I can ask a sort of what's I guess a very mundane question. I mean, you focused at the beginning on price per watt.
Yep.
And a related aspect of that, I guess, is square meters per watt. Simply because we've only got so much land that we can use for these applications, and that comes through with these. So I'm guessing that a bigger motivation for your sort of triple junction devices is actually it's the square meters per watt. So that's a comment. My question is about recycling. I mean, you've focused a bit on durability, but they're not going to last forever. One question is how likely it is that they will last as long as silicon. But the related question is how afterwards, whether there are any challenges in terms of recycling them with the various materials that you've got.
I mean, that's an interesting question, because I think we've come to a point in the silicon technology perspective where they're coming to the end of their lifetime, a lot of the big, and that's become a huge aspect where people are looking into how do you recycle a silicon panel. With perovskites, the interesting fact is, it's like a double-edged sword. The fact that they can be processed so easily, but they can also be recycled as easily, in the sense that because they're soluble in solvents and they can actually be, they're akin to low temperature annealing, and you can actually anneal out the organics and let's say, and then just remove the inorganic components, that aspect makes them really attractive. Now, another aspect is, well, if they can be made so easily and if they can be recycled so easily, can they be destroyed in climate, in the environment as easily? And right now, yes. I mean, they're not thermostable. I mean, they have shown that they can be stable for a year. However, we're talking about a year compared to 20 years that silicon has. And even after 20 years, silicon still does well. It's just that they lose a set amount of efficiency that they've set as a standard. So that's where the community is now working quite heavily on not only developing new packaging routes to package the solar cell, but actually intrinsically making the material more stable by adding larger cations. So, for example, I showed that the crystal structure is adept at I can just show you the slide. The crystal structure you can change such that, hold on. Okay, so the crystal structure here, you can actually change these A-site cations into phenyl groups or aromatic rings, which are actually hydrophobic. And so essentially, if you cover that top layer of a material with a hydrophobic A-site cation, then the material actually becomes really much more stable. And so there are all these routes that we're trying to implement to make the material more stable in the environment. But in terms of recyclability, these are all readily soluble in solvents, and sadly also readily soluble in water. So yeah, that's the double-edged sword, I guess. Thank you, David.
Thank you for the question. It was a very interesting point because I think when thinking about net zero, we kind of look at the whole cycle, right, of the technologies and of the materials. So this, I think, was a very interesting question. Is there any other question from the participants? Yeah, please. I'm not sure I can say your name correctly. Sorry, Ashfaq Alam.
Yes, can you hear me?
Yeah, we can hear you.
Yeah, you have said it perfectly. Thank you.
Okay.
So my question is regarding the possibility of mass production of this type of devices. You have already mentioned that the conventionally perovskite solar cells are basically fabricated using spray pyrolysis or spin coating, things like that. So normally for roll-to-roll technique, when it comes to mass production, it's very suitable. But you're using PVD. So do you think it is suitable for roll-to-roll technique when it comes to mass production?
Do I think it's well, industry is now somewhat matured in this particular aspect of time in terms of perovskites, and the industry is moving towards dry techniques. And the reason for this is, yes, solution techniques work, but in terms, it's not shown to replicate what you get. Solution-based techniques give the world record in the lab. But when people have tried to replicate that into the larger scale using inkjet printing or spray pyrolysis, they've not been able to replicate such success. Whereas PVD has not shown the highest of efficiencies, but reliably, when it's gone into a larger module size or industry, it's shown to be of a good efficiency reproducibly. Another thing to note, which is key, is in multi-junction devices, when you go to roll and using solvents, you need solvent orthogonality. So when you have so many different layers, you need to make sure if you deposit the perovskite with an X solvent, that X solvent doesn't interact with the preceding layer and dissolve it. Now, you completely mitigate that with a PVD. And so with PVD, you don't have to worry about that. There is no infiltration and damaging of the preceding layer when it comes to manufacturing.
Thank you, Dr. Patel.
Thank you for your question as well. So is there any other questions? So I want to ask you more of a general question in the framework of this interdisciplinary series. So my question is, how do you think this your research, I mean, maybe what you presented today or more generally your research could benefit from collaborations with other maybe departments or other colleagues outside physics? So do you have any idea of maybe a possible collaborations or topics that could help you maybe or us to expand the remit of the research?
Yeah, I think with this technology, with perovskites and solar, it's now reached a point where, because it can be developed on so many different substrates, you can actually look at applications. A good example is agrivoltaics. You know, this is something where people have been looking into the food versus fuel argument. Is like in areas where there's a lot of population and a high density population, what do you use your land for? Do you use it to generate electricity or do you use it for fuel? And I think this is a particular area where perovskites, which you can make so that it's semi-transparent, you can actually generate electricity whilst growing crops. Also, so that this in itself paves the way for me to work with people who work in land management or people who are agriculturalists to actually see, okay, what do you guys need in terms of growing crops? And here's something that we can develop in the technology to actually, when it comes to trying to reduce net zero, we don't want to actually reduce the amount of food we produce because, you know, global hunger is also a thing. So, you know, it's not just a one facet challenge, it's multifaceted. Yes, we're trying to achieve net zero, but how can we make sure that we, on the road to meeting net zero, we don't forget about the other challenges that already exist in the world. So I think that's where, you know, I've been talking to the Department of Geography, then there is people in the policy world out there who, you know, are interested into seeing how new technologies can actually be implemented. When it actually comes to the faculty itself, there is engineers in the sense that I would like to know, you know, when it comes to durability, how they test their particular materials and how I can interact with them. They might have ideas on plastics in terms of chemistry, how does plastic degrade and what type of plastics you can use to recycle, etc. So the scope is large and it's just trying to find the individuals that do things.
Yeah, thank you very much. This was very highlighting and you raised quite a few points. We have now Declan who wants to ask a question.
Yes, thanks. I just wanted to follow on with another question about interdisciplinary links. I'm just thinking about the business side because there's a lot of technologies needed for net zero. Just however good they are only taken up quite slowly because the economics of investing into factory production, workforce training, and so on mean that companies really want to get value from the current generation batteries or solar cells and so on. What it wasn't, this may have been clear to people who are more expert than I am, but I wasn't clear whether once a company moves into large-scale manufacture of perovskites, is a shift from 2-junction to 3-junction easy, or does it mean investing in a whole new set of sort of factory equipment and so on? And so, what if you like the economic investment steps that people might need to go up to adopt these at scale?
I think that's a really interesting question. I think essentially silicon has existed. As you can see in the PowerPoint, silicon has existed. Now, as soon as you get tools that you can make perovskites on top, then you don't need to change the equipment at all to develop any numerous amount of junctions that you want. So the capital cost of that, once it's done, it's done. Then it just becomes the knowledge aspects of it. And that's where the research and innovation comes in. That's where universities come in, and that's where you need to have links with industry, right? If I have the tool to develop this material that they're using in the industry, then anything I do here, they can instantly put it into their tool because it's just one tool that develops the whole structure from single junction, double junction, and triple junction when it comes to perovskite.
Declan, do you have any follow-up?
No,
Or?
no, thank you. That was what I was hoping the answer was. That sounds really good.
Thank you.
Thank you. So we have still a few minutes. I see now questions in the chat. So hopefully maybe this you can answer quickly. There are 3 questions now. So the first one is from Raul. Is technology readiness level for this PV technology?
So Oxford PV recently bought the manufacturing plant, Bosch Germany's manufacturing plant that used to develop PV silicon photovoltaic panels, and they've started to develop perovskite silicon multi-junction devices. They've not released it to the market, but in conferences where you go, they've now started to show stability tests that they've done. So it seems like it's imminent that they will release a product with the silicon and perovskite. So that's where the TRL is for perovskites as a whole. Triple junction, I mean, we're still a bit far off. But if we actually get triple junction to work even within the 10 years, then you'll be talking about technology that's 2.5 times better than what exists right now. So that's a huge step.
Thank you. I agree. There is another question from Massimo. What role do computational methods play in developing this technology further?
Okay, that's super interesting. So the computational methods help us in the sense that, as you can see, there are lots of different components that we could put into this crystal structure whilst maintaining the Goldschmidt tolerance factor, which makes sure that the perovskite stays a cubic structure. And computational physicists and chemists especially have tried to develop different compositions that not only result in a perovskite that absorbs light, but also is more stable. Or, as you can see from the slide here, we use lead. How do we move away from lead? Like, we've already started to think about that. How can we move away from having the lead as the core metal component? What other materials that we can put? And so computational methods essentially give us what we should be aiming for next in terms of a material class.
Thank you. There is another question that maybe it's a bit related to the previous one. Market readiness. So what is the market readiness?
As I said, it should be in. They've shown that there's a product. They've bought manufacturing plants. So I'd assume, and companies in China are also showing much larger panels. So it seems like it's nearly there. Maybe end of this year, maybe next year. I don't know. I don't have a company, unfortunately.
Perfect. Thank you very much. So I think I don't see any other question. Just want to check if there is one very last quick one from anyone. No. So I think we are getting close to the end of the seminar, and I want to thank you very, very much for this interesting talk and for the discussion, and also thanking the audience for these great questions that cover a bit of different aspects, not only the physics aspect of this. I want to conclude also by saying that if you are interested in giving a talk to this seminar series, please get in touch with me or with the center manager, Lydia Sandiford. I also want to thank Lydia very much because she's behind all the organization of today. So thank you very much to her. And again, look forward to see you at the next seminar, who will be given by a colleague in mathematics, Claudia Neves. Thank you again, everyone, and I will see you soon. Bye.
Thank you. Bye.